Hello everyone. In this video, we will be discussing about electric discharge machining process, flushing types and its process parameters. So, we know that one of the important factors in a successful electrical discharge machining operation is removal of debris, which is also called as chips from the working gap. In case if you are not removing the chips properly from the work surface means that will be deposited on the workpiece and that leads to the further sparking, and finally we could not able to get the exact shape or the output what we are looking for. So flushing out these particles from the working gap is very important, so that it will prevent them from forming extra bridges, and even that may lead to the short circuits. Electrical discharge machinings have a built-in power adaptive control system that increases the pulse spacing as soon as this happens and reduces or shuts off the power supply. So flushing process of introducing a clean filtered dielectric fluid into a spark gap. So for this we have provided a proper filter and we have a pumping setup with an dielectric fluid tank. So whatever the fluid which takes or which carries away the debris from the tank, that will be stored in a separate temporary tank, and that will be pumped back to the like a filter. From the filter, like all the debris will be collected and immediately that will be removed, because since it is a continuous process, that debris should be removed instantly. And if flushing is applied incorrectly, it can result in erratic cutting and poor machining conditions. So that is why it should be removed immediately with the help of a flushing. So flushing of dielectric plays a major role in the maintenance of stable machining and the achievement of close tolerance and high surface quality. So inadequate flushing can result in arcing, decreased electrode life and increased production time. And here when we speak about the flushing, we have four major methods. First one is the normal flow, second one is the reverse flow, third is the jet flushing method, and fourth one is the immersion flushing. So if you look at the major components of this flushing means, as usual, usually like one electrode we have seen in the sketch, but in the real time application, two electrodes, three electrodes, multiple electrodes will be there. Okay, so if this is the electrode means, and the shape of the electrode where we are getting the same shape in the workpiece. When we speak about the normal flow, like towards the gravity, where the dielectric fluid will be allowed to pass through the inlet and it will be flushing out in the side of the electrodes. And moving to the second one, reverse electrode, where the dielectric fluid will be pumped from the downside, that is which is the direction opposite to the gravity force, and where from the sides the dielectric fluid will try to enter. So you can able to see this. So most of the cases we will be recommending normal flow, where dielectric is introduced under pressure through one or more passages in the tool and is forced to flow through the gap between tool and work. Flushing holes are generally placed in areas where the cuts are deepest, and normal flow is sometimes undesirable because it produces a tapered opening in the workpiece. And moving to the second one, reverse flow, particularly useful in machining deep cavity dies, where the taper produced using the normal flow mode can be reduced. So the gap is submerged in filtered dielectric, and instead of pressure being applied at the source, a vacuum is used. So with clean fluid flowing between the workpiece and the tool, there is no side parking and therefore no taper is produced. Moving to the third type, jet flushing. In many instances, the desired machining can be achieved by using a spray or jet of fluid directed against the machining gap. So machining time is always longer with jet flushing than with the normal and reverse flow modes. And the last flushing method is nothing but immersion flushing. For many shallow cuts or perforations of thin sections, simple immersion of the discharge gap is sufficient. So cooling and debris removal can be enhanced during immersion cutting by providing relative motion between the tool and workpiece. Vibration or cycle interruption comprises periodic reciprocation of the tool relative to the workpiece to effect a pumping action of the dielectric. So generally, electrical discharge machining flushing, it synchronizes the pulsed flushing is also available on some machines. So with this method, flushing occurs only during the non-machining time, as the electrode is retracted slightly to enlarge the gap. Increased electrode life has been reported with this system. Innovative techniques such as ultrasonic vibrations coupled with mechanical pulse EDM, jet flushing with sweeping nozzles, and electrode pulsing are investigated by Mazuzuwa in 1990. So for proper flushing conditions, metal handbook is recommended, which says that flushing through the tool is more preferred than side flushing. Many small flushing holes are better than a few larger ones. Steady dielectric flow on the entire workpiece electrode interface is desirable. Dead spots created by pressure flushing from opposite sides of the workpiece should be avoided. A vent hole should be provided for any upwardly concave part of the tool electrode to prevent accumulation of explosive gases. A flush box is useful if there is a hole in the cavity. So the waveform is characterized by the open circuit voltage VO, the working voltage VW, and the maximum current IO, the pulse on time, the duration for which the voltage pulse is applied, T on, and the pulse off time it is T off. So the gap between the workpiece and the tool, it is a delta, that is spark gap, and the polarity where straight polarity tool, which is negative, the dielectric medium where external flushing through the spark gap. And the process parameters, if you see, means where it is represented with respect to the time and the velocity. So we can able to T off and T on, which is nothing but the pulse time off and pulse time on, and with respect to the time, even the current also flow, and we can able to see the curves in the amplitudes. So sinker EDM, also called cavity type EDM or volume EDM, consists of an electrode and workpiece submerged in an insulating liquid such as oil or other dielectric fluids. So the electrode and workpiece are connected to a suitable power supply. The power supply generates an electrical potential between the two parts. As the electrode approaches the workpiece, dielectric breakdown occurs in the fluid, forming a plasma channel and a small spark jumps. So these sparks happen in huge numbers at seemingly random locations. As the base metal is eroded and the spark gap subsequently increased, the electrode is lowered automatically so that the process can continue. Several hundred thousand sparks occur per second, with the actual duty cycle carefully controlled by the setup parameters. So these controlling cycles are sometimes known as on time and off time. The on-time setting determines the length or duration of the spark. Hence, the longer on-time produces a deeper cavity for that spark and all subsequent sparks for that cycle. This creates rougher finish on the workpiece. The reverse is true for the shorter on-time. Off-time is the period of time that one spark is replaced by another. A longer off-time, for example, allows the flushing of dielectric fluid through a nozzle to clean out the eroded debris, thereby avoiding a short circuit. These settings can be maintained in microseconds. The typical part geometry in a complex 3D shape, often with small or odd shaped edges. And EDM types: wire EDM, also known as wire cut EDM and wire cutting. So a thin single strand metal wire, usually brass, is fed through the workpiece, submerged into a tank of dielectric fluid, typically deionized water, used to cut plates as thick as 300 mm and to make punches, tools, and dies from the hard metals that are difficult to machine with other methods. And this, if you see the metal removal rate, so metal surface quality, accuracy, pulse characteristics, crater volume, and thermal properties and tool electrodes plays a important role in the metal removal rate. So we can just see the effect of pulse current energy with respect to the metal removal rate and surface roughness. So moving to the surface integrity, where the surface consists of a multitude of overlapping craters that are formed by the action of microsecond duration spark discharges. Crater size depends on physical and mechanical properties of the material, composition of machining medium, discharge energy, and duration. And depth of craters, the peak to valley maximum surface roughness, where the maximum depth of damaged layer can be taken as 2.5 times of roughness. So average roughness can be expressed in terms of pulse current, that is amperes, and pulse duration µs. So thus, in turn, in increased workpiece melting and created greater expulsive forces that increased metal removal rate and surface roughness. Choice of a correct dielectric flow has a significant effect in reducing surface roughness by 50%, increasing the machining rate and lowering the thermal effects in the workpiece surface. And metallurgical changes temperature starting from 8000 to 12,000 degrees Celsius, and a thin recast layer of 1 micrometer to 25 micrometer. And this sketch we can able to see where the recast 1 to 40 micrometer, hardened 200 micrometer, and anneal 200 micrometer. So with this All these link removal of altered layers by low stress, addition of metallurgical type, reheat treatment, and application of short peening gets completed. Thank you.